write down a few important things under the heading of notes. We discussed about the Young's double slit experiment. What was happening? There was light that was passing through two slits. We named them to be S1 and S2. And when they passed through the slits, they created on a screen an interference pattern. The central line, the central spot that we see, it's going to be a bright spot. And this bright spot is called the first bright fringe. The one that is on top of it is called the second bright fringe. The one that's above that is called the third bright fringe, but the central line is often called the zero order maxima. The one that lies above it is called the first order maxima, and the one that's above it is called the second order maxima. We'll talk about maximas more in diffraction grating, but what I'd like to add here is that uh, imagine this was the cardboard slit through which the light was passing, and this here was the screen on which we were observing the maximas. The one that is exactly in front of the center, the central bright fringe or the zero order maxima, and on either side of that there were dark areas, and then there were more bright fringes, and then there were more dark areas on either side. Now, every now and then we will see a question that will arise about intensity of light. On the y-axis, there is intensity, and on the x-axis, there will be displacement. So, at positions corresponding to maximas, you will be observing the graph that will look like this. There will be increased intensities, and then there will be areas where the dark fringes are formed. That's where the intensity is going to be lowest. What did I do here? I am actually noting down the intensities at different positions on the screen. Let's say if I note down the intensity at this point and then plot the intensity value correspondingly on a graph which had intensity on the y-axis and displacement on the x-axis, at this point the intensity was going to have a minimum value. Where there is a maxima or a bright spot created, that's where you will see the graph of intensity to increase to a maximum value. And then after that, the intensity is going to drop again as we continue to move along this line. The maxima that is exactly at the center, it's going to have the maximum intensity. So the central maxima will have maximum intensity. Maximum intensity. Why? Because the central maxima or the central bright fringe is the shortest distance away from both the slits. Okay, that means when the waves reach this point, the waves, they will not have a they will have the largest amplitude that they can have. But for any other maxima, like for this position or a bright fringe, the wave that is coming from one of the sources and the wave that's coming from the other source, they have traveled a further distance as compared to the central position. So as they reach this maxima, their amplitudes would have decreased further, because we know that as the wave travels, its amplitude continues to decrease. Its amplitude continues to decrease. So the maxima or the bright fringe formed at the center is where both the waves will reach and their amplitudes will not have decreased as much. But for the maximas that are formed away from the centers, if you look at them, the waves reaching those maximas, they have traveled a further distance. Let's say like for this one, this maxima, wave coming from S1 and waves coming from S2, they have traveled a further distance as compared to the central position. So their amplitude may have decreased a little more than as compared to the central position. So the maxima that will be formed away from the center, they are going to have slightly less intensity. They are going to be slightly less bright. So I will write this down here. Central maxima is the brightest. Central maxima is the brightest. Then the ones forming on either side of it, this one and this one, they will be slightly less bright than the central. And if I continue to increase this displacement graph, that means if I continue to plot the pattern of maximas and their intensities, I will see the amplitude slowly keeps decreasing. The maximum intensity for this maxima, you can see it's smaller than the central maxima, and then there will be a dark spot again, and then there will be another bright spot, but this time the intensity will have a slightly smaller value, because as the maximas continue to grow away from the central position, that's when their brightness keeps decreasing, and that's where their intensity keeps decreasing. Do you understand that?
Yeah, I got it.
Okay, that's great. I think I'd have to move this even more. All right. Another point that I'd like to tell you here is if one of the slits is completely covered, if one of the slits is completely covered, that would mean there is no interference pattern is formed. No interference pattern is formed. That's because in order for interference to take place, we actually need two waves from two light sources. But if one of the source is completely covered, that means light is only passing through one slit and it's not passing through the other slit. So in that case, there will only be one light source. The other light source is not able to interfere with the first one. So there will be no interference pattern formed. Okay, there is something else I'd like to add to this graph. Wherever there is a dark fringe or a minima being formed, there the intensity is minimum but not zero. Intensity is minimum but not zero. What does that mean? We remember that intensity was directly proportional to the amplitude square. Wherever there is a minima formed or a dark spot that is formed, waves are unable to completely cancel each other out. Why? Why are they able to not cancel each other out completely? Because one of the waves at a maxima would have traveled more distance as compared to the other wave coming from the other source. So that means if one wave has traveled more distance, it would have lost its amplitude, it would have lost its energy slightly more than the other wave. Imagine I'm using a green color for this. Imagine for this maxima, this is a light, no, sorry, this minima, the dark spot. This is the light source coming from S2 reaching this minima, and another light source is coming from S1. It is reaching this minima or the dark fringe. You can see the wave coming from S1 would have traveled a further distance as compared to S2. So that means when S1 reaches the minima point or the dark spot, this is where the waves coming from S1 will have slightly shorter amplitude as compared to the waves coming from S2. That means, let's say the wave that reached here had an amplitude of 2.3 centimeter and the wave coming from S1 had an amplitude of 2.2 centimeter. So they are not going to completely cancel each other out. There will be some amplitude still remaining. That is why a dark fringe is not actually going to be completely black. It's going to be dull. It might have some light in it, but it will be dull as compared to the brighter fringes. Do you get that? Does that make sense?
Could you repeat this again?
Okay, I'll write it down for you. Waves meeting at a minima won't, instead of minima, I will write a dark spot. At a dark spot, destructively interfere, but can't completely cancel out because one wave will have traveled a longer distance than the other. So longer distance than the other. So that wave will have shorter amplitude than the other. Shorter amplitude than the other wave. We know that if a wave travels a distance and if it travels more distance, its amplitude is decreased to a greater degree. So for a minima being formed, two waves meet destructively, but because one wave will have traveled a slightly longer distance than the other wave, so one wave will have a slightly shorter amplitude than the other one. So when they try to completely cancel each other out, but they don't have equal amplitudes, so they end up only decreasing the amplitudes instead of completely canceling it out. So that just means dark spots are not completely black. Dark spots are not completely black. They are very dimly lit spots, but their intensity is non-zero. But at dark spots, the intensity is non-zero. Is it any better?
The last point doesn't really make sense.
The intensity of not being non-zero?
Dark spots are not completely black. They're like
Okay.
they are. What's that word, sir?
They are very dimly lit. I will improve that for you. Dark spots are not, as they are very dimly lit spots. I'll explain it, no problem. Imagine if there is a dark spot being formed here. This is a wave S, this is a source S1 and this is an S2. One wave travels from S2 and reaches this point. Another wave is traveling from S1 and reaching this point. This is only logically true that wave coming from S1 has traveled a longer distance and wave coming from S2 has traveled a shorter distance. Let's say at the beginning, both of them had an amplitude of 6 centimeters. That means the waves they were creating at the beginning had an amplitude of 6 centimeters. But because wave coming from S1 has traveled a longer distance, so the wave that reaches from S1 till this point will have a shorter amplitude as compared to the wave coming from S2. Let's say because S2 is closer to this point P, the amplitude that reaches from S2 is, let's say, 5 centimeter. And the amplitude that reaches from S1 till P, amplitude S1, that's going to be less than 5. So that means a wave that has an amplitude of 5 centimeter is trying to destructively interfere with a wave that has an amplitude of 4 centimeter. Do you see that these two waves won't be able to completely cancel each other out? There will still be an amplitude of 1 centimeter left after they destructively interfere. So if there is a
Oh,
non-zero amplitude left after destructive interference, that would suggest that there will be a non-zero intensity. Make sense?
all right.
Hey, excellent.
Took me a while, but all right.
Sorry,
I said it took me a while, but all right.
it's okay. It's all right. These are weird things. We haven't studied these things before, so yeah, they often trouble the students. Okay,
No, it was really confusing. I just needed it to like sink in.
yes, it's all right. Even if you want me to repeat it, I'll repeat it for you whenever
No,
we
I
talk
got
about
it.
solving few questions. Okay, there is one thing I'd like to add more to the interferences, and then we'll move on. Uh-oh. Right. Now, another point. If one of the slits is partially covered, the interference pattern is still observed, but bright fringes are less bright and dark fringes are less dark. What does that even mean? Let's say these were the two sources of light, S1 and S2, and this was the interference pattern forming. If I partially block one of the slits, partially block, that means it won't be able to allow the complete amplitude of the wave to pass, the complete intensity of the wave to pass. But one of them, the S2, is completely allowing the waves to pass. In this situation, there will be a bright fringe at the center, then there will be dark fringes on either side, then there will be a bright fringe on either side, and then dark fringes on either side again. But this time, you see, initially S1 was contributing complete waves. Complete waves means they were S1 was contributing a higher amplitude of a wave. But now S1 is contributing a shorter amplitude of the wave. That's why when the waves meet at maximas or bright spots, they are not going to completely add up to the same intensity as before. That means, let's say S2 had an amplitude of 6 centimeter and S1 is allowing an amplitude of 3 centimeter. So when they pass, of course, they are going to lose some energy. So the wave coming from S2, let's say it has an amplitude of 5 centimeter. The wave coming from S1 was, let's say, 2 centimeter. So now their combined amplitude is going to be 7 centimeter only. Imagine if I don't cover the S1 slit. In that case, there will be 6 centimeter of amplitude, and then when they meet at a maxima, when they meet at a bright spot, S1 would be contributing more energy to the bright spot. In that case, bright spot would have been brighter, but now S1 is only contributing half the amount of energy. So at the bright spot, the bright spots are not going to be as bright as they were before. And the dark spots which were formed, they're also not going to be as dark, because wave coming from S2 has more energy, the wave coming from S1 has less energy, so they are not going to be able to cancel each other out. That way the dark spots are still going to be a little brighter as compared to before. Does that make sense?
Yeah, it does.
Okay, that's great. These were the few things I wanted to add to interference, because I was teaching it at another place and I encountered a few questions. I thought I'll share them with you as well. Okay. Should we get back to our discussion about the diffraction grating?
Yes.
Okay, that's great.
So is this topic fully done now?
Yes, interference is done. Double slit interference is done.
All right.
Now, for diffraction grating, it was just a piece of glass or plastic that had some small holes in it, a lot of them. And those holes were actually mechanically made. That means it was a glass plate, and machines were used to construct these scratched lines on them. Each line behaves like a small hole. In our previous discussion, we talked about two slits, but in this discussion, we are talking about many. How many? Around 500 lines per centimeter. I have called them holes previously because we were trying to relate it to the double slit interference. Actually, they are lines, and these lines behave like holes. So these lines are so close to each other that in 1 centimeter there are about 500 lines. Okay, so a diffraction grating it's not something that we have made using our hands. It's a mechanical device. Okay, it has been constructed mechanically by using machines. So this is what a diffraction grating is represented in a diagram. When waves are passing through the diffraction grating, every opening here will behave like an independent source of light. Even though all these holes are illuminated from light coming from the same source, but all these holes, when light shines on them, every hole is going to allow diffraction of light that's going to look like this. Initially we had only two holes, but now we have a lot of holes here. Okay, at the center there will be a maxima or a bright fringe formed. This is called a zero order maxima. Zero order maxima. And then there is a minima on either side. A minima is formed where a destructive interference takes place. The one above it, this maxima, will be called the first order maxima. The maxima that is below the central maxima is also called the first order maxima. Then there are more maximas on either side. This one is going to be the second order maxima. Second order maxima. These are just their names, which are referring to their positions above the central line. So this central line, the imaginary central line, has an importance in our discussion. Imagine the first order maxima here. That means the maxima that is formed exactly above the central maxima. I join the central line and the center of this maxima with another straight line. Okay, both these red lines, they are imaginary lines. There is no line at the center, there is no line. We are just drawing it on a diagram to indicate an angular value. The central line is being used as a reference, and I am joining the central line with the center of the first order maxima by using a straight line, the angle that's formed between them is called theta. Okay, there is an equation for diffraction grating. D sine of theta equals to n into lambda. This equation is given in our question paper. D sine theta equals to n lambda, where theta is the one that I have shown you in the diagram. I'm going to describe theta here for you as well. It is the angle formed between the lines drawn at the center of grating and center of maximas. This point here, I'm calling this P. This P point is the central position on the diffraction grating, and the dotted line at the center is the line that is horizontal, and it is joining the diffraction grating with the center of the zero order maxima. And then I have constructed another line here that is joining the point P and the first order maxima. These are just construction lines. They won't be there in real life. These are just numerical, these are just lines drawn to actually give us theta. Then there is n. N is the order of maxima. Then there is lambda. Lambda is the wavelength. Wavelength is supposed to be in meters. Order of maxima can be 0, plus minus 1, plus minus 2, plus minus 3, and so on. N simply indicates if it is the first order maxima or the second order maxima or the third order maxima. And D is the gap between two lines. Do you understand all the variables in this equation?
Sir, plus minus y.
Because the ones...
Is it because the ones above the line are
Yes.
plus and the ones below? Oh,
Yes, exactly. For here, n is equal to 0, the central first order. Here, n is equal to plus 1. And the one that lies below the central line, it has n equal to minus 1. Okay.
all right.
The second order that lies above the central position, for that n is equal to plus 2. And if there was a maxima, second order maxima forming below the line, for that n is going to be equal to minus 2. Okay. All right. I'm going to show you an example from this equation so that we know how to actually apply this. This is a very popular question. Examiner will show you things on the diagram like this. Okay, this is the central position. Examiner gives you this angle to be equal to 70 degrees. Examiner tells you that the wavelength is 600 nanometers. Examiner tells you that here the order of maxima is 0, here the order of maxima is plus 1, here the order of maxima is n minus 1. Basically, n plus 1 maxima and n minus 1 maxima, they are identical to each other. It's just that one lies above and one lies below. All right. You have theta, you have wavelength, you have order of maxima. They ask you to find out d. So you just recall that d sine of theta equals to n lambda. You need to find out d, and instead of theta, what are you going to place? Now, this is a common misconception. Examiner gives you the angle between both the first order maximas, but this is not the one that has to be used in the equation. In the equation, we only use half of it, because when we were discussing the equation, I defined theta with the point of view of the central line. Okay. So if examiner gives you 70 degrees, you have to use 35 degrees in the calculation. So instead of theta, you will place 35, n will be 1, and the wavelength is 600. Nano stands for 10 raised to power minus 9. So the d comes out to be 600 into 10 raised to power minus 9 divided with the sine of 35. If you just solve that, this would tell you what is the gap between two lines on the diffraction grating. Do you understand that?
Yeah, I got it.
Okay, that's a very common question. You might have to calculate this for what, like 3 marks at least.
3 marks for this?
Yes. With
That's nice.
one little variation. I'll show you what that variation is. Okay, if this is okay so far, should I move on?
Yeah.
Okay, here is a note for you, something important. Small d is equal to 1 divided by capital N. What is capital N? Capital N is the number of lines per meter. Gap, D is what? D is the gap between two lines. D is the gap between two lines, and N is the number of lines per meter. Number of lines per meter. That means how many lines are present on 1 meter of that glass strip. Sometimes there are 500,000 lines per meter. In that case, D, the gap between two lines, is going to be 1 divided by 500,000. That's going to be the gap D in meters. This is an important relationship. Examiner will, most of the times, examiner will not give you the small d. Examiner will give you the number of lines per meter. So you have to recall that d is going to be equal to 1 over n. I will show you the logic behind it. Okay, let's try to understand that. One line over here, this line, the first line here, this line is making a gap from the edge, that is d. The second line is making another gap from the first line that will also be equal to d. The third line will be making another gap from the second line that is also equal to d. The next line, the fourth line, will also be making a gap between the third and fourth that will be equal to d. So if in 1 meters there are 500,000 lines, then a gap, then a line of then one line is actually making up a gap of d meters. Once more, in 1 meter there were 500,000 lines. Then one line is responsible for making a length of d, one small d. I would rephrase that. Inside 1 meter of length there are 500 lines, and one line is formed after every d meters. So you just cross multiply them. That's going to give you 1 into 1 equals to 500,000 into d. From here, d comes out to be equal to 1 divided by 500,000. Do you remember 500,000 was, they were the lines per meter. So this gives us that d must be equal to 1 over capital N, the number of lines per meter. If this doesn't make much sense to you, you can simply substitute 1 over n instead of d in this equation. 1 over the capital N. Are you with me so far?
Yep.
Okay. Now, a lot of students lose their marks because examiner isn't always going to give you 500,000 lines per meter. Sometimes examiner gives you 500 lines per millimeter. In that case, you would have to convert lines per millimeter into lines per meter. I'll show you what I mean by that. If it is 500 lines per millimeter, a milli is basically 10 raised to power minus 3. So that means I can write it as 500 lines per 10 raised to power minus 3 meters. This 10 raised to power minus 3 goes on in the numerator and it becomes 500 into 10 raised to power plus 3 lines per meter. Basically 500 into 10 raised to power plus 3 is again 500,000 lines. So in some cases, examiner can give you lines per meter. In other cases, examiner can give you lines per millimeter. Okay, so if it's lines per millimeter, you should convert it into meters. That's all I'm trying to tell you. Okay, any question?
No.
Okay, that's great. I'm going to show you one more thing for today. This is a concept. Okay, this is a concept and it's a very frequent question. You will expect it for 3 marks. Okay, you'll see how easy it is, but 3 marks is what it's going to be worth in our paper 2, sorry. The maximum number of maximas. The subtopic is the maximum number of maximas. We just recall the equation, that is the d sine theta equals to n lambda. Here, n is the order of maxima. Okay. During one experiment that is being performed, d and lambda, they are constants. We know that n can vary from 0, 1, 2, 3, and so on. And when n varies, theta also varies. When n varies, theta also varies. So this tells us that n is directly proportional to the sine of theta. Now, if I want the maximum n, sine theta should have a maximum value as well. For max value of n, sine theta should also have a maximum value. What is the maximum value of sine theta? The maximum value of sine theta is 1, and it occurs when the theta is 90 degree. That means the angle of diffraction is 90 degree. That's when sine theta has its maximum value. And that's exactly where the maximum order of maxima should be formed. I'm going to explain that to you in a minute. Okay. Now, this is the diffraction grating, and light is passing through the diffraction grating. Okay. We know that the zero order maxima is formed exactly in front of the center. Okay. And as the angle theta continues to increase, what could be the maximum value of the sine theta? What could be the maximum value of theta? See, from the central line, the maximum angle can be 90 degrees. That means when light passes through this edge, it diffracts exactly along the boundary. That's the maximum value of angle there can be for diffraction. So I'm going to construct a curved screen here for your benefit. Okay. In center, there's going to be a maxima. Then there is going to be minimas or dark areas. Then there will be maximas as well on either side. Then there will be more minimas. Then there will be maximas. Then there will be another minimas. And then there will be maximas. So you see, the maximum angle for which a maxima can be formed is at 90 degrees. So in order for finding out the maximum number of maximas, we need to place theta equals to 90 degree. This is n equal to 0, this is n equal to 1, this will be equal to n equals to 2, and this is n equals to 3. N being the order of maximas, order of maxima is 1, 2, and 3. This 3 means this is the third maxima above the central line. And this n equals to minus 3 means it's the third maxima below the central line. Okay, so when you place theta to be 90 degrees, sine 90 automatically reduces to 1. From here, the maximum number of maxima above the central line will be equal to d divided by lambda. This n will be the maximum number, yeah, maximum order, I should say, order of maxima above the center. This is how we can find that out. Wavelength is known, d will be known when you divide it. That way you'll be able to find out the maximum number of maximas being formed. I want you to appreciate this, that maximum maximas and total number of maximas, they are two different things. Okay, maximum number of maxima is what we calculated by this formula. Examiner sometimes asks you to find out the total number of maximas. What does that mean? Total number of maximas will be found by 2 times n plus 1. I'm going to explain why I am using this equation. N is the maximum number of maximas above the central line. Maximum number of maxima above the center. When I multiply it with 2, that gives me the number of maximas above and below the central line. And when I add plus 1 to it, this is the 0 order maxima that is forming at the center. So that way you will be finding out the total number of maximas, the ones that are forming above the central line, the ones that are forming below the central line, and the ones that are forming at the center of the at the center line. So this one is added because we are trying to count the total maximas. For that, we would have to count the central maxima as well. Do you understand that?
Yeah, I got it.
That's great. Here is
Sir,
some.
could you write
Uh-huh.
right beside the last one you just told me right now? Could you
Okay.
write it beside one? That since
Okay.
we have to calculate the middle one.
Since we have to count the central maxima as well. That's why we add 1 to 2n. Okay.
All right.
All right. There is one more thing. There is one more technicality about this I'd like to add here. While calculating n, if n comes out to be 3.42, 7.92, 8.99, these are just random values that I'm choosing. Ignore the decimal value. Ignore the decimal values. Just use whole number. Just use whole number. That means from if the n that you calculated came out to be 3.42, you will only be using n to be equal to 3 and ignore 0.42, because examiner will be asking you the number of complete maximas. That means 3 maximas are completely formed and 0.42 of a maxima was also being formed, but that 0.42 will not be counted as a complete maxima. In case of 8.9, n will be equal to 8, and you will just ignore the value of 0.99, even if it is almost a complete maxima, but it is still not a complete maxima. So you will just consider the whole number in your calculations and ignore the value of decimals. In mathematical terminology, we call it truncation. Truncation means ignoring the decimal values, not rounding off. If I had to round it off, 8.99 should have become 9, but I am not rounding off, I am truncating it. That means ignoring any and every decimal value formed after a whole number. Do you understand that?
Yeah, I got it.
If after calculation you end up getting a value of n that is not a whole number, you will ignore the value of decimal and just use the whole number for it. Is that okay?
Yep.
All right. Okay, that's pretty much it about diffraction gratings. There will be one more thing that I'll tell you in the next class. That's going to be about the diffraction of white light. And then there will be stationary waves from this chapter, and then this chapter is going to get concluded. I'm just going to write down a heading here: diffraction of white light. Diffraction of white light. This is what we will discuss in our next lesson tomorrow. After that, we'll have quite an extensive subtopic of stationary waves, and then this chapter will be over. Okay?
Okay.
All right. Would you like to give a test this week?
Yes, I would.
Which chapter would you like me to test you on?
Kinematics.
Okay. I'll share a test with you. When? On Sundays or Saturday?
I think Sunday's better for now.
Okay.
If something doesn't come up, then.
All right. Definitely. I will try to remember